In this video, I want to just talk through the remaining limit laws in the book. They basically cover information that I've already given you, but just in a slightly different form. So remember, the first 5 limit laws dealt with our arithmetic operations. We've got 4 arithmetic operations: addition, subtraction, multiplication, and division, but we had 2 versions of the rule for multiplication. We had a special case of if we were multiplying by a constant, and then another rule for if we were just multiplying 2 functions. But basically, those limit laws said that we could interchange the order of things. We could do the arithmetic and then take the limit, or we could take the limit and then do the arithmetic if we were combining functions via arithmetic. Well, Rule 6 and 11 are going to add to the list of things that we can interchange the order of doing those things with taking a limit. Okay. These are other things besides arithmetic operations. They're algebra operations, but things that we can do, and we can do them first and then take the limit, or we can take the limit first and then do them. I should mention the only significance to Law 11 being off to the side here instead of below the others is just that I ran out of space. Okay, so Law 6 has to deal with taking powers. So here I've got a function f of x, and I'm taking it to the nth power, and then I'm taking the limit. The law says I can take the limit first, and then I can take the nth power. So I can interchange the order of raising something to a power and taking the limit. Now, your book specifies that n has to be a positive integer. That's what this means right here. That fancy z means the set of all integers. When I put a little plus sign on it, it means we're talking about positive integers. Now, that's not to say that this is only true if n is a positive integer. In fact, I've told you that this is essentially true if n is a fractional exponent, so that we're taking roots. Okay? It's actually going to be true for all powers as long as what we have is defined. So I know I can't take the reciprocal of 0. I know I can't take an even root of a negative number. But if this doesn't lead to nonsense like that, then it's going to work. The book is just telling us this for positive integers because at this point they can explain why that's true. If n is a positive integer, then raising something to the nth power is just multiplying together n factors of that thing. So Rule 6 is true, and we know that because it's just repeated application of the product rule for limits. I've told you it's true even if n isn't a positive integer, but in that case I can't explain why it's true at this point because it's not as simple as just repeatedly multiplying things together. Okay. Law 11 talks about taking roots. So here we're taking the nth root of a function and then taking a limit. That's going to be the same as taking the limit first and then taking the nth root of that. Now again, here they're specifying that this holds for positive integers. That is not to say that that's the only time that this is true, just that that's all they're telling us right now. Okay. They do have this qualification: if n is even, then we're going to suppose that what's underneath here is positive to avoid the problem of taking an even root of a negative number, which we can't do in the real numbers. So we do have to qualify this a little bit to say, hey, it works as long as we're getting something that makes sense. Okay. Rules 7 through 10 basically just tell us that certain types of functions are continuous without using the word continuous. Remember, I've told you that if a function is continuous at a point, like at an x value a, then you can take the limit by simply evaluating the function at that point. You evaluate the limit by plugging a into the function. So Rule 7 says constant functions are continuous. If I take the limit as x goes to a of a constant function, I can just evaluate that constant function at a. And of course, if I evaluate a constant function anywhere, it gives me the same constant. Law 8 says the identity function, y equals x, is continuous. So if I take the limit as x approaches a of x, I can just evaluate that function at a, and of course that's going to give me a. Law 9 says that power functions, where the exponent here is a positive integer, are continuous. So if I'm taking the limit as x approaches a of x to the n, I can just plug in a for x, and I get a to the n. Again, this rule is true even if n is not necessarily a positive integer. It's true if n is a fraction, it's true if n is irrational, it's true if n is negative, as long as we avoid the situations of trying to take the reciprocal of 0 or trying to take an even root of a negative number. Okay? But very often, if we were proving all of these things, it would be easier to prove things in the case that n is a positive integer, and then to use that result and some other stuff later on to prove the other cases. So I think that's why the book is breaking it down. I just wanted to mention that when they say n is a positive integer, all they're doing is saying this is true if n is a positive integer. They are not saying it is not true if n isn't a positive integer. And in fact, the next rule is talking about taking nth roots of x. That, of course, corresponds to powers that are 1 over n, so fractional powers for certain fractions, and that's continuous. If I'm taking the limit, I can just plug in a. Okay. And we do have this rule that if n is even, a is going to have to be positive. Now here they're saying a has to be positive. That means a can't be 0. And I want to just look at one important thing. If I wanted to take a look at the limit as x goes to 0 of the square root of x, that's actually not defined. Because with no notation here, that's a two-sided limit. And I can't take the two-sided limit because my function only exists at 0 and to the right of it. So I would have to say this is taking the limit as we approach from the right. Okay. And then I can just plug in 0. It's the square root of 0, and it's 0. Okay. So they don't include that case here, really to avoid having too many sort of caveats and footnotes about, oh, by the way, if this happens, it's a one-sided limit. But I did want to point out that, yes, this function, as long as you're coming in from where the function is defined, we're still going to be able to evaluate it by simply plugging in. And when we get to the section on continuity, we'll define what's meant for continuity and distinguish between endpoints of a domain like 0 here and points that are in the middle. Because if you're at the end point, it simply doesn't make sense to take a two-sided limit. You've got to be taking a one-sided limit. Okay, so those are the other limit laws as they're presented in your textbook. Again, the qualifications that they give do not mean those are the only circumstances in which they're true, but they're telling you, hey, this is in fact true.